Testing, testing. 1, 2, 3. 1, 2, 3. Okay. Hopefully we are live now. And today we're going to be covering some problems related to integral calculus. The very first problem is given an expression that looks like Jn of a is equal to integral of 1 over x squared plus a squared to the n. It's asking us to calculate for base cases of j0 and j1, which should not be so bad, right? When n is equal to 0, the denominator just sort of turns into 1, something raised to the 0th power. So this just turns into the integral of 1 dx, which is the easiest integral there is. So then for the case where n is equal to 1, you have the situation where, how do you put it? Let's rewrite it. X squared plus a squared, which looks a heck of a lot like the arctan integral. Arctan. So go look that up in your textbooks. And the only issue here is that the a is not quite the same thing as the 1. So the way I would probably rewrite this is just to sort of pull out an a squared out in front, which basically turns this into a 1 and turns this x into an x over a. X over a squared. Yeah? So hopefully you should be able to see how this correlates to the arctan. It's just going to require an extra application of chain rule because it's x over a instead of just x, or a reverse chain rule perhaps. And apart from that, if you are struggling to see it, then maybe you can just do a change of variables with u is equal to x over a, and see if you can use substitution to make this a little bit more clear. But okay, now on to the main meat and potatoes of the problem, is to figure out how to, given that you have integral of Jn, try to figure out a way to write integral of, try to write Jn plus 1 in terms of Jn. And I think it's implicitly understood that you want to rewrite it such that there are no explicit integrals involved at the end. You want basically to express Jn plus 1 as some blah, 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 blah times Jn. You don't want to write any integral signs. And this is kind of an annoyingly, kind of a computationally intensive problem, as well as one that kind of requires a trick or two, integration trick or two. So I've figured out 2 different ways to do it. And they're both a little annoying. So let's just go through the process a little bit and see which one you like more. Okay, so for one of them, I'm going to write that Jn is equal to, well, I'm just writing it out, x squared plus a squared, n plus 1 times dx. So let's call this method 1. Yeah? The idea here is that you play around with it a little bit and you manage to get a Jn plus 1 to pop out if you start with integration by parts, right? I know that we're sort of already given what Jn is, but I'm going to rewrite it in a couple of different ways using integration by parts, and you'll kind of see how we get a Jn plus 1 to pop out of it, and then we isolate for Jn plus 1. So basically the idea here is to make this u and to make this dv, right? With integration by parts, you're totally allowed to just make the dv to be just the differential x on its own. So, okay, u is equal to 1 over x squared plus a squared to the n plus 1. Sorry, why did I write n plus 1? It should just be n, because it's jn, right? Then du turns into, what is this, minus n over x squared plus a squared to the n plus 1 times, I think, 2x. Sound about right because of chain rule. And then dv is equal to dx, so v is just equal to x. Well, okay, I will continue on a little bit more because I want to show you how this, this is starting to kind of look like the jn plus 1, but I'm going to massage it a little bit more to hopefully make this a little bit more clear. So remember, jn is equal to, by the integration by parts formula, just look it up in your textbook, uv minus integral of v du. Yeah, it's going to turn into x over x squared plus a squared to the nth minus a negative sign. So it's going to subtract a negative sign, so let's just write it as a positive, right? There's a negative sign from integration by parts, canceling out with this negative sign over here, and it turns into, let me write the 2n out in front maybe. It turns into 2n x squared divided by x squared plus a squared times n plus 1. And yeah, this is where a slightly obnoxious, slightly inspired trick has to come into play. But you can rewrite x squared as x squared minus a squared plus a squared, right? This is called adding a smart zero, is the cute little name for it. Adding a smart zero. And it's totally reasonable, right? You can always add a zero to whatever you've got. It's still going to be the same thing. It's just going to somehow turn this into something a little bit simpler for us. But let's just look at it when you write it as x squared minus a squared plus a squared, right? So I'm not gonna write out everything again. I expect you to do that on your own. But what does this turn into? This turns into two parts, right? This turns into x squared minus a squared over, oops, I wrote it the wrong way. X squared plus a squared minus a squared, right? Because the whole point of this is that we want to get some cancellation in the first side, a squared over x squared plus a squared to the n plus 1. Yeah, there's a term in the top that looks a lot like a term in the bottom, so we get to cancel we get to cancel the plus 1 basically. And then we have to subtract out a squared over x squared plus a squared to the n plus 1 dx. Right. So at this point, this thing here is basically just 1 over n, x squared plus a squared to the n, right? Which is jn. And over here, it's looking an awful lot like, well, the a squared is just a constant you can pull out front. And it's a squared. So this turns into essentially minus a squared times jn plus 1. You see that? So what I would suggest you to do is just drag everything back down. Be super careful in your calculations, your computations, whatever. And notice that you've got some jn's here, and you got a jn plus 1 here. So solve for your jn plus 1 and see what you get. All right. So that was the first method. Let's take a look at a second method that well, it's not that different, but it's a little different. You can figure out which way you like best on your own. So I think this time around we're starting with the expression of jn plus 1 is equal to 1 over x squared plus a squared to the n plus 1, right? So last time, there's no way ahead of time that I, knew to start with jn here instead of jn plus 1. It just turned out that way. As you sort of work through it, you realize it's convenient to start with a jn there. But with method 2, it's convenient to start with a jn plus 1, right? So you don't have no way of knowing ahead of time. It just required some playing around with it. But the trick here is to essentially do the same adding and subtracting trick, but to rewrite this first as 1 over a squared times a squared, right? This is just multiplying top and bottom by a squared over a squared, which is 1. Totally legal, right? So then now 1 over a squared times the integral of a squared plus x squared minus x squared, right? The same trick of adding a smart zero. And, this time I'll rewrite it as two separate fractions from the get-go. X squared plus a squared to the n plus 1 dx. Yeah. So from here, you should be able to see that this is going to result in some nice cancellation like before. Yeah, and once that cancellation is done, you're left with the integral of 1 over x squared plus a squared to the n, which is just in, or rather jn, right? And as for over here, with the x squared over this stuff, if I remember correctly, you can figure this part out using integration by parts. Yeah, so let's just rewrite this a little bit as integral of x squared. Sorry, my handwriting is getting kind of cramped. But you can always, when you're subtracting two terms inside the integral, you can always just split the integral apart into two, because the integral is a linear operator. Look that up if you don't know what that means. But okay, so you can rewrite this as x times x over x squared plus a squared to the n plus 1. And once you have that, well, all your problems should be hopefully solved at this point, if I'm not mistaken, right? Let me look at my notes. Yeah, at this point, I think this is screaming U substitution, because this looks like a really nice dv. Yeah, this part like is really nice to integrate on its own. X squared plus a squared to the n plus 1, because you can kind of see this. You can basically do substitution, right? Look at this x squared plus a squared in here, and look at this x sitting nicely on its own. It's a perfect candidate for substitution. Whereas x dx, whereas u is equal to x is the other part. This is your u. And that should just be great. That's du is equal to dx. So go through and, solve this out. And I think it should be quite similar to before, where, okay, so you have jn plus 1 here is equal to all this crap. And I think you're going to end up with some jn's and jn plus 1s on the right-hand side. And you're going to end up needing to isolate all the jn plus 1. That's probably what it's going to look like. Actually, I don't even know. I didn't solve this one all the way out myself. But if there is some jn plus 1s on the right-hand side, just isolate it out. If not, then you're probably golden. I actually don't know that off the immediate top of my head. Yeah, but looking at this right here, the integral of this should look something like blah, blah, blah times 1 over x squared plus a squared to the n. Right. There might be some negatives. There might be some factors of a half or n in there. But this is looking pretty nice. And actually, maybe there is not even going to be any jn plus 1s on the right-hand side. But anyways, the goal of this is not to do all the homework, but to sort of just show you the tricks and show you the tools of the trade so that you can do it on your own. And of course, when doing integration by parts, never forget to drag down the other stuff that you had before, right? Don't just forget about it. I have a bad habit of doing that. Anyways, that should cover problem 1. I think it was maybe one of the most involved ones on the set. But let's do problem 2 now. Ah, yes, almost as involved, this one. So what I found for this was, I didn't even know that this was true. And honestly, I can't really visualize this very well. But what this is sort of saying is that x minus s, f double prime of s, ds, right? So what this is saying is that, like, if you have some, like, starting point for a function, let's say it's doubly continuous, right? Let's say f at 0. What this is kind of saying is that, like, if you want to evaluate f of x at, well, x, the idea is that, okay, you're going to take the tangent line, you kind of take the tangent line at 0. So this slope right here is like f prime of 0. And it's sort of like you're saying you're adding in an extra correction factor, right? You're sort of writing the slope up for some distance x, which will get you over to like here. And then the double prime stuff will give you this extra correction factor to get you exactly to f of x. And that might be kind of intuitive, kind of not. But it definitely took me a little while to see this. And I think the way to start this problem is to just write out what you know from the fundamental theorem of calculus, where, what is it? Fundamental theorem of calculus is going to tell us that f of x is equal to, well, maybe let's put it this way. F of x minus f naught is equal to the integral of f, what do you want to call this? Fs ds from 0 to x. Gosh, I should really clean up my notes a little bit. Okay. And of course we have this because it's it's continuous second derivative, so we can write this for both fundamental theorem of calculus for both the first and second derivatives. F prime of 0 is equal to 0 to, well, hold on. Because this is an this should have been an f prime of s. And because this is using an s, I want to use an s over here to kind of make that notation consistent. So now it's going from 0 to s of f double prime of, now we already are using x and s, now let's use t. Right? We kind of call these things dummy variables or variables of integration that kind of only exist in the scope of the integral. But looking at this now, you can kind of move the f primes over to the right-hand side. Sorry, the f prime of 0 and f of 0 to the right-hand side to sort of get this, just sort of adding it, right? And adding it instead of subtracting it. So what we're seeing here compared to what we want is, all right, f of x is equal to f naught. Okay, so far so good. Plus f prime naught of x plus all this stuff with a double integral. All right, so the first thing I'm thinking is let's just go ahead and try to plug this in here and see what happens. Yeah. So if we try to plug that in there, that f of x turns into, I'm just copying this down, f naught plus 0 to x of f prime of 0 plus, this is sort of like all in the integrand, 0s f double prime of t dt. And you're kind of noticing that we're having an iterated integral, which you typically don't see until multivariable calculus, but I guess you're being presented it here. And I think that's a ds, right? All we've done is just plug in for f prime of s. So what we can do now is essentially distribute this integral across the addition. And we could do that because, again, the integral is a linear operator. The integral of a sum is the sum of the integral. So what we get here is 0 to x, f prime of 0, ds, plus 0x, 0s, f double prime of t dt, ds. So if you want to, you can just, if you don't really want to think about an integrated integral too deeply, you can just kind of think of this as like some function of s that once you figure it out, you just plug into the integrand of the outer integral, right? Just sort of think of it one integral at a time. But okay, so that's what it's equal to so far. And now it's looking pretty good, right? Because this f prime of 0 is literally just a constant, right? It's literally just some number. That does not depend on s or x, really. This basically just turns into multiplication, right? Because remember what this is. If you have something that just looks like some value of c, and it's going from 0 to x, well, the area under the curve is just cx, right? So this just becomes f prime of 0 times x. And lo and behold, that's exactly what we were hoping we would get, right? F prime of 0x. So now all we have to do is account for this last term somehow, and of course this last term is the doozy. Somehow we've got to massage this and turn it into that monstrosity. And honestly, I don't have any good way of visualizing why this works. I just had to play around with integration by parts and found that it just turns out right. But what I tried was, I said just let this entire thing in the brackets be equal to u, and let's let dv be equal to ds. And of course, v is equal to s, and u is equal to 0s t dt. So at this point, you basically just take the derivative with respect to s, right? And by the fundamental theorem of calculus, that's sort of like just plopping the s inside, right? The derivative and the integral sort of cancel, is sort of what the fundamental theorem of calculus tells us. So now it looks like f double prime of s ds. Right, you got rid of the integral. So yeah, at this point, I would suggest you to try to carefully conduct the rest of this through using integration by parts, right? You're going to do uv minus v du. And you should hopefully find that it starts to look a heck of a lot like the end result. Yeah. And remember that at this point, when we're doing integration by parts, right, uv minus v du, it's going to be from 0 to x, because the integration by parts is to do the outside integral. Yeah, so hopefully that's not too confusing, but I don't think I should say anymore. I think I should let you figure out the rest on your own. But use this u, v, and v du to do this, and what you should find is that it's going to look mighty similar. And at the end, what I noticed was that I got two separate integrals, and one of the integrals looked like x 0x of f double prime of t dt, And I think the other one was like 0x and, well, you know what? I probably shouldn't say everything. But the point was I had one integral that was in terms of t and the other integral in terms of s. And what you notice is that you can just combine them just fine, right? Like each dummy variable is limited to its own scope. So there's no reason why you couldn't just relabel the t and call it an s as well in order to make them congruent with each other. So go do integration by parts, carry that through, and hopefully you get something good. Okay, part 3 is almost a qualitative question. So provide an example of an indefinite integral that, when integrating, requires sine of x as a substitution. Well, yeah, okay. So I would ask you to possibly consider some composite functions, right? Let's maybe just think of some function like an exponential, or like a, I don't know, exponential, a polynomial, whatever, g of x, and then just instead of doing g of x, maybe just do g of sine of x, and see if you can, like, I feel like saying too much kind of gives this one away, and I feel like this is not one of the harder ones on the set. It's just more conceptual. But just find a way to integrate, you know, maybe use an exponential, right? Just insert the sine of x. Sorry, replace x with sine of x, and try to set up the integral so that the chain rule is also accounted for. What I mean by that is when you have u is equal to sine of x, right? Du is equal to cosine x dx, which means that we kind of want to reverse engineer our integral to have a cosine x floating near the dx somewhere, right? Whatever else you do with the function involving sine, I would really suggest that you have a cosine x dx, cosine x near the dx. Anyway, that's all I'll say on that one. Okay, so now we have one that I think this one is actually fairly intuitive, unlike the others. This is basically saying that g of x dx is equal to a plus b over 2 of g of x plus g of a plus b minus x dx. And this is just kind of annoying, right? But what this is saying is, if you have some like integrable function, maybe let's just call this a, and let's call this one b, right? What this is basically saying is that, all right, if you just integrate it all the way through, that would get you some area that looks like this, right? But what you could do instead is you could possibly break it up into two parts, right? Exactly the halfway point, which is like a plus b over 2. So this is a, this is b, and this is the midway point, a plus b over 2. And what this is sort of saying is that the integral of, what the heck, g of x over from a to a plus b over 2 is sort of this part right here that I've already shaded. And it's sort of like saying, show that the rest of this stuff is equal to g times a plus b minus x from a to a plus b. How do you put it? It's kind of intuitive, right? Like this a plus b minus x thing, going from a to a plus b over 2 is kind of like, oh, I'm sorry. Sorry, what's the best way to say this? Wait a minute, something's just a little bit funny. Something's just a little funny. A to b, and a plus b over 2 is the exact midpoint, right? I don't know. This thing right here, I haven't thought about it too hard, but it's sort of like, I guess it's sort of like counting backwards, maybe? Yeah, because x has to start from, right, because you're counting backwards, right? The first value of x that you get is a, and it goes from a plus b over 2. So yeah, when you sort of think about that, right, it's sort of like saying it's counting backwards, because a plus b minus x at the lower bound of a just turns into b, so it's starting right here, and it's sort of counting the area backwards, so to speak. And you can kind of see that between these two regions here and here, it's sort of adding up to the original region. And it should feel pretty intuitive, I hope. But to actually show this, you're going to want to how do you do this rigorously? You're basically just going to want to split this thing up into two integrals from a to a plus b over 2 of g of x, and a plus b over 2 to b of g of x dx. And you're going to just want to just like massage stuff around a little bit, do some change of variables in order to show that this thing can be equal to that thing over there. Yeah, that's probably all I should say about that. But yeah, keep in mind that this is equal to, like, how do you put it? Keep in mind that you can flip the top and bottom of, Man, it's kind of hard to say anything without giving it away. But I would suggest trying, like, I haven't solved this all out myself, but I would suggest trying to replace x with like a plus b minus x and see if you can figure something out with that. Yeah. Okay. All right. It's I don't know. It's conceptually it's not hard, but it's kind of finicky to do the actual math. But hopefully it should be intuitive. All right, so the next parts I don't really feel like I can offer any advice on. It's just some really, really dense calculations using partial fractions and whatnot. I think I checked the final answer with an integral calculator and it didn't seem like anything was off, so I don't know, maybe it's just some like tiny piece of step somewhere that's wrong and you just have to read it carefully. I don't know, somehow maybe they did something unjustified and or maybe made like an error that somehow didn't end up mattering, because it seems like they had the right answer at the end, but maybe they, I don't know, make a mistake that cancels out with itself or somehow. Just see if you can go through it and find something, because I don't think it's very educational if I just pour through some dense text, right? But similarly, I guess for part 6, just try to follow the approach, and for part 7, given the results of part 5, and say that you want to integrate 1 plus t to the 4th squared. Yeah, I think you could probably just do integration by parts, right? dt, well, that's exactly what they suggest, because you would know how to integrate this part if it was just on its own, right? Like 1 over 1 plus t to the 4th squared. Would you? Yeah, I actually haven't thought about this one. I just assumed referring to the previous part would make things go fine. But yeah, how do you want to do this integration by parts? What's the ideal split? I haven't thought of it myself, but one way you could split it is u is equal to t to the 4th, and dv is equal to 1 plus t to the 4th squared, or 1 over this dt. And I don't know, this isn't the nicest, right? Because this doesn't really quite allow you to reuse the part from part 5, because that was for 1 over t to the 4th. So maybe this isn't the right split, because I don't really know how to integrate this off the top of my head. But maybe if you tried a different split, like u is equal to t to the 4th over 1 plus t to the 4th, and then dv was just 1 plus t to the 4th dt. Integration by parts is, I would say, kind of an art, maybe more so an art than a science. And sometimes you just have to fumble around a little bit and see what will let you make progress. Sometimes you just have to wander around in the dark a little bit. But I would say that this doesn't look so bad. This doesn't look so bad at all. If you did, if you took the derivative of this, what would you get? Is this bad? T to the 4th over 1 plus t to the 4th squared times 4t cubed. I guess there's a negative sign in front, but I don't really care that much. Okay, and then what does v turn into? V turns into all that nasty crap before. Yeah, this is, hang on. ln of t, arctan. Yeah, this is not so promising either. There are other splits we can try. What if we tried u is equal to 1 plus t to the fourth? Or rather, let me rewrite the integral. We can rewrite it as like, oh, let's move the 4 in front. Doesn't really matter, right? 4t cubed times t dt. And what if we just did 1 plus t to the fourth squared? So what happens here? So I cook this up because I think this makes for a nice substitution pair, right? Because you have a t to the fourth on the bottom and t cubed up top. And then we can just let u be equal to the t by itself. This thing right here, this is u. So then dv is equal to t cubed over 1 plus t to the fourth. Maybe this will be nice. Yes. I think this is quite nice. Because then v is just going to look... Okay, so this is a squared, right? And then v will look something like 1 over 1 plus t to the fourth to the just first power. It might have some constants in front. I don't really care. Figure that out carefully for yourself, right? But then once you do integration by parts, you do uv minus integral of v to u. And suddenly with this and this, you can reuse the result of part 5, and it's going to be super nice. So this is just maybe a little confidence building exercise, integration by parts, where you just have to try out a couple of things, and sometimes it's not obvious what split will be the perfect one to defeat the problem, so to speak. Anyways, we continue onwards. Now we have pi r squared. We're trying to figure out the area of a circle. Yeah? And I'm trying to think about it now, but it's hard to remember back to middle school, but did they ever actually prove to you why the area of a circle is pi r squared? Did they? Honestly, I don't think I remember ever learning that. I just took it for granted when I was younger, and it wasn't until calculus where I think I learned it. But okay, if we're letting this be r, the idea here is just to calculate the area of the top half, right? Because you don't really know how to do polar integration yet. And because the circle cannot be represented by a single function, f of x, because it doesn't pass the vertical line test, right? Let's just ignore the bottom half and just integrate the top half instead. And then by symmetry, the bottom half must, of course, be the same area. So far, so good. So with this in mind, if this has radius r, the equation for this thing is basically x squared plus y squared is equal to r squared. So let's solve for y in terms of x. That's y squared is equal to r squared minus x squared. Then y is equal to plus or minus r squared minus x squared, right? And we're going to take the positive because the minus corresponds to the bottom half that we decided we're not going to deal with. We're only going to deal with the top half. So yeah, that's what this is. Y is equal to, the top half is described by this equation. And we're taking r to be a constant. Like r is fixed, the size of the circle, x and y are the variables. But the idea is, okay, well at this point, you just want to integrate y dx, which is equal to, from, I guess, minus r to r, which is just r squared minus x squared dx. And to do this, I think this requires a inverse trig integral, if I'm not mistaken, because this is not so easy to integrate just directly. But look at your list of inverse trig integrals and see if you have something that looks a lot like this. Keep in mind, actually, do you? I hope I'm not lying to you. What the heck? Yeah, it's been a while since I've looked at this, and I just vaguely remember this has something to do with an inverse trig, but maybe that's a total lie. It's possible. how would I integrate this? Oh, maybe not inverse trig. Maybe it's just some of the other trig functions. Like, yeah, it's coming back to me now. Right, so sine squared of x plus cosine squared of x is equal to 1. So maybe do 1 minus cosine squared of x is equal to sine squared. And maybe let's call this like u instead of x's, right? Yeah, it's a trig sub integral. So the idea is if you can, right, you could kind of pull out an r to make it look like r times 1 minus, I think, x over r squared, right? But if you just do a substitution where cosine of u is equal to x over r, I think you should be able to figure this out. And I would take a good look at maybe a trig sub integral in your textbook to figure out the process, because it's kind of involved and I don't want to give away everything. But that's the idea, right? You would let cosine of u is equal to x over r. And once you do the substitution, and don't forget to do your chain rule, I think what you would find, so this is dx, so then minus sine of u du is equal to dx over r. What's really nice about this is that at this point you could turn this integral into, well, 1 minus r times 1 minus cosine squared. We've established a sine squared u dx, right? And then you could just turn this into the integral of sine u dx. Yeah. And then when you sub in this dx, I think you're going to have to pop out another sine of u with a substitution, but I'm hoping that you can possibly carry this forwards and figure that out. Yeah. If I remember correctly, at some point, well, it looks like you're going to get an integral of sine squared at some point. And for that, I would consider using the, you have some identities for that, right? I think there's a double angle formula for cosine. Double angle formula, where cosine of 2x is equal to, what is it, like 1 minus 2 sine squared of x? Go look it up. I don't remember it off the top of my head. I think it's this way, but I might have the signs backwards. So double check that and see if this will be useful in terms of, because it's hard to integrate sine of squared of x directly. And what this is saying is you can turn it into a cosine instead, which is much easier. Anyways, figure out the rest on your own. I think that's the gist. Yeah, so for the next one, we're talking about a surface of a revolution. Y is equal to 9 over x squared plus 9. Y is equal to 0, x is equal to 0, x is equal to 3. So what is this saying? I think this looks kind of like sort of just a hill, right? And it's saying between y is equal to 0, okay, x is equal to 0, and x is equal to 3. So I guess it's sort of like saying you take this and using the washer method, find the volume of Q. Okay, so it's basically, I'll erase the rest. It's basically saying just use the washer method, just sort of rotate it around, right? To get a solid. And to go, I mean, I feel like you've already done a bunch of these problems, haven't you? The washer method. But the basic idea is to break it down into a bunch of washers, which are basically like infinitesimally thin cylinders, right? So if this has some cylinder with some height dx and some area, the area of the circle is basically going to be pi y squared, right? The sum of, the total volume of the entire thing is going to be the sum of all the little volumes, right? All the little chunks of volumes. And each little chunk of volume is basically going to be pi y squared times, I'm going to call it, sorry, why am I using y? sorry, pi y squared times delta x, right? Because y dictates the radius of each of these circles or washers, and x dictates the height. And the area of a cylinder, of course, is pi r squared times the height. So this is radius and this is height. And okay, we're just subbing in for y, right? We had some expression for y. We'll just sub in for that thing. And then we turn this into an integral. So this looks kind of like 9 over x squared plus 9 squared dx, right? And the limit, the sum, and the delta turns into an integral. Yeah, double check all this work and carry it out for yourself, but I think that's the gist. And yeah. Figure that out. Looking at this might require some sort of trig sub integral. Off the top of my head, this looks like right, this plus sign is kind of screaming for us to use what is it, like tan squared of u plus 1 is equal to secant squared of u. The only thing is, like before, you might want to pull out a factor of 9 here to make it look a bit more like tan squared u plus 1. Right, so pull out a factor of 9 and it'll look like x squared over 9 or something like that plus 1. So yeah, get good with your trig sub integrals. Okay, so those were a couple of routine problems, but now we're back to an interesting one. And this is a pretty famous result, and it's called orthogonality of sine or cosine. And the deal here is that, okay, why did I write pi? This should be an m. If m and n are equal to each other, I think it's pretty clear that this is just, going to turn into a sine squared integral, and those are nice and predictable, your good friend. But the issue is that, or at least that's from negative pi to pi, but the most curious thing happens when m and n are different integers. And we actually find that, this is a famous result, and it doesn't really give away the answer because this problem is more about the proof than the answer, but like the famous result is that it's equal to 0 if n is not equal to m. And we kind of got to show that, prove that. And what I would suggest doing is just saying, all right, let's let this integral be equal to I, and then do integration by parts with just arbitrarily saying u is equal to sine mx, and dv is, I keep forgetting that, sine of nx dx. Yeah? And go through and do your integration by parts, and you're going to find that I is going to be equal to some expression of cosines, I believe. Cosine mx, cosine nx, and there might be a bunch of factors here, either on bottom or on top. And then it's going to subtract out some integral of... I'm sorry, this is probably more like... I think I got that wrong. The term outside the integral is going to be sine of mx times something like cosine of nx. Yeah. And, okay, minus, and there's going to be some like constants here, and here. And I think the integral is going to look like cosine x, cosine mx, cosine nx, dx. And the idea is if you integrate this again, then this splits into another term that I guess is probably going to be, it's going to look like this one, but in reverse. It's going to be cosine mx, sine of nx, times some constants, blah, 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 blah. And the most curious thing happens is that, of course, you get the original integral again, which is like sine of mx, sine of nx. And the idea here is that if I is equal to, all this stuff plus the original integral here, with some constants in front, right? It might be a factor of like n or m or whatever. And what's really special about this is that as long as this coefficient is not equal to 1, right, then this is just some factor like c times I, right? And then you can just move this to the other side and then isolate for I and solve, right? But you're going to find the really special thing that happens is that when n is equal to m, this factor is going to be equal to c. Sorry, c is going to be equal to 1, I think is what I found. And when that happens, this I and this I cancel out with each other. Cancel, cancel. So it turns out that this method is not going to be useful for the case where n is equal to m. That's why you got to special case it. But whenever n is not equal to m, this method will let you go through and find an expression for I. So just to reiterate, you can move I to the other side, right? This turns into a const C. This turns into a Ci plus I. And then you can just solve for I, because at this point it's an algebra problem, right? And what you'll notice is that if you evaluate this from pi to negative pi, you should see the result that we were talking about earlier. You should see the orthogonality I was talking about. Orthogonality means some product comes out to be 0, essentially. Yeah, so this is a very common trick in integral calculus, and I didn't really know a name for it until pretty recently. But the idea is, after you do some integrating, the original integral kind of pops up in your work, right? It kind of rises from the ashes. And apparently the Germans like to call this Phoenix integrals, which I think is a really cute name. We should make it a thing. I kept forgetting it because I didn't have a name to associate it with it, but it's a trick that you see somewhat commonly. So just remember, if you see the original integral pop up again, and as long as that factor isn't exactly equal to 1, then you should be able to solve for it. Okay, all right. Now we continue. So, yeah, this next problem was very cute, right? So what's the arc length formula? It's sort of like the integral of 1 plus dy over dx squared, I think, from whatever, for whatever range in question. And if I remember correctly, just writing out some of these things, it was sort of like there was a function y of x, and there's a function y prime of x, and they're related by some differential equation. It just takes a bunch of work to parse through the very cute language. But I think it's saying that y of x squared plus y prime of x squared is equal to 1. And it's also saying that the integral of fx is something, right? The function satisfy an antiderivative is a function calculus whose domain is also R. So, okay, basically some antiderivative exists, right? Instead of f, let's say y. Yeah. So the antiderivative exists, and it has a name. So the idea here is, if you can just recognize that y prime of x is the same thing as dy dx, this is basically saying that you can use these facts right here. Sorry, was it a plus or was it a minus? I feel like I've missed by a sign here. Something's off. Ah, yes, this should be a minus, right? What you notice is that if you just move this to the other side, you get exactly this thing right over here, right? 1 plus y prime squared, which is to say that you can replace this thing on the inside with just y of x squared. And now things are looking really pretty, right? The square root and the square cancel out, and you should be able to figure out the rest from there. And remember that you're told that some antiderivative exists, and you're told that it has some name, right? Compute the arc length. There are some other details for you to sort out on your own, because you're told that compute the arc length of the curve y if for all x from 0 to b, where b is a positive constant. Yeah, I think you need to think about that a little bit, maybe. Yeah. Actually, I'm not even sure why b is necessarily important for this one. Does it tell you something about the constant of integration? Not totally clear, to be honest. I kind of find that vague. Anyways, I think I've said enough. You can think about the rest on your own. But yeah, we're coming to an end here. So what's next? So now we're talking about a differentiable function and a positive number. Yeah, I think that these are pretty root problems at this point. The surface of an area obtained by rotating. Right, this is a surface area thing, right? So if this is y of x, I usually have to go look this up, but there's basically just some formula for it, right? And the idea is that if you rotate this around and you're not trying to calculate the volume but the surface area, I don't know really how to draw this. The idea is that you can't, like, a cylindrical approximation doesn't quite work out nicely because, like, there's some little slopes in here that don't quite get accounted for, right? It's like a little bit different from calculating volume. It's a lot more like calculating arc length when you're trying to find the surface area. And what is this, over some domain from like A to B? Okay. But the idea here is that you have some arc length formula that ought to look like, what does it need to look like? Where is it? Well, maybe you should just find that for yourself. I don't exactly have a textbook on hand. Surface of revolution. I mean, it should just be some equation. It looks a lot like the arc length thing. I think it just, off the top of my head, it's kind of like pi y squared times 1 plus y prime squared, maybe? Does this ring a bell? I'm not confident about this, so you got to double check it. Yeah. ds. Oh, no, sorry, not pi y squared. Why am I doing... Yeah, no, that's wrong. I'm trying to find the... basically what this is saying is... if you can find the perimeter... Not the perimeter, the circumference of each one of these circles, right? So if the radius is y, then the perimeter becomes 2 pi y, right? And it's basically saying 2 pi y times... let me explain it. It's basically 2 pi y times some small ds, and ds is basically like this change in, like a little differential change in the curve, right? It's similar to your arc length parameterization. But the issue is this ds is not exactly the same thing as x, because sometimes if, you know, it's tilted at a bit of an angle, then ds is longer than the corresponding dx, right? So that's why you got to basically put in this correction factor. Got to put in this correction factor that's like a square root of 1 plus y prime squared. And the justification for it is from the arc length explanation. So yeah, after that, just plug in the expressions for y and y prime and integrate, and you should be good to go. Yeah, I think that's probably all there is to say on that one. Yeah, this one was a little harder, but more fun than the rest. Yeah, I think this was very fun. Area of a surface. Yeah, I'd be surprised if this is like, I'm pretty sure this should just be in your textbook, right? This is a surface area of revolution. I feel like this was definitely something in my textbook. I took this. But all right, I think that does it for today. Yeah, if this was helpful, I'd appreciate it if you took a moment to like, subscribe, and perhaps comment. Engagement with the channel helps it grow, and possibly helps more students discover what I do in the future.